welcome back. And it looks like nobody left. That's good. So for the second hour, we will be talking about recurrent neural networks, which are a completely different architecture. And please welcome Nithum Thain, who works at Google Jigsaw. And in a minute, he will tell you what he does. You will see it's interesting. But first, let's dive into these different architectures called RNNs. And first of all, I don't know if you have been on Google Translate lately. You know, Google Translate has been around for ages, and it has this reputation for being, you know, what is used to produce the badly translated manual in your Chinese electronics. But really, try it again. Try it again. Let me show you this. Devoxx is a conference organized by computer enthusiasts. And this is actually 100% spot on. It even translated passionné de l'informatique, which is how you say this in French, into a completely different expression, which is computer enthusiast, which is how you say this very specific thing in English. And this is down to, of course, more data and more work and so on. But mostly, these advances come from better neural network architectures. And what we want to do today with you is go through a couple of recurrent neural network architectures, which are the architectures used in Google Translate or other language problems, and show you the advances that have been made, and mostly show you what is called an attention mechanism. But first, what is a recurrent neural network cell? So by now, you should recognize here a neural network. We have inputs. We have a layer of neurons. Those neurons still do the same thing. They do a weighted sum of all inputs, add a bias, feed this through an activation function. And at the end, I have my softmax if I want to classify something. Now, the specificity of recurrent neural networks is that we do this. This middle layer, of course, it has outputs that will go down to the next layer. But the same outputs, I also take them out and reconcatenate them with my inputs in the next time step. So this is something that will be working in time step. I have one input at time t, I feed it through the neural network, it gives me some output, and it gives me some output, and it gives me, and the intermediate layer also gives me an output, which I'll use as a state vector for the next time step. And the way in a given time step, I combine my input vector and my state vector from the previous time step is that I simply concatenate them before running them through my neural network. So this can be represented schematically as a cell with one input, one output, one input state, and one output state, which usually is passed around. And also, traditionally, the softmax layer is represented outside of the cell by this yellow circle here. Okay, so the green box only represents those green neurons here. So it's a state machine. It has a state that is associated to it. And it is going to be very good at processing sequences of things, like sequences of characters or sequences of words. How do you train it? Well, as usual, you take your inputs, you feed your inputs into your neural network. Your neural network uses weights and biases to produce something. You say, no, that's the wrong answer. You compute the difference between what it said and the correct answer. You retropropagate, change your weights and biases, and yeah, that works if your weights and biases were the problem. But here we have this additional input state. What if you are producing a bad answer because your input state was in some ways bad? Well, you're stuck. So to get unstuck, the solution is to replicate this cell multiple times. It's the same cell with the same weights and biases replicated, and you will still be stuck with the first input here. But if you say, for instance, that H2 has some dodgy values in it, you have all the weights in this cell to work with to produce an H2 that has better values. So unrolled, you apply a sequence of inputs, you go through the network, produces a sequence of outputs, and then you force a sequence of correct answers to that, retropropagate, and that's how you train the system. But you will always have this limitation that you need to unroll those recurrent cells in a sequence, and that sequence will still have a limited size, and that size will be a limit to your training. Anything you want to teach the system will have to be taught on examples of that limited size. And that's something that is inherent in this architecture. Okay, what if you want to go deep and have multiple layers? Well, actually, if you stack two cells like this, still the same API, you can say this is one cell. It has still an input, an output, an input state, an output state. Those states are a bit bigger, but it's still the same API. So that's a very easy way of stacking multiple cells to go deep, and to learn through this system, you unroll it exactly in the same way. The cell itself, one thing that people noticed is that this tends to be a very deep neural network. You enter data here, and it has to cross this neural network and this one 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 until it reaches this value and produces something. So recurrent neural networks, and of course you want to unroll as much as possible because you have this limitation that you can only teach it tricks on training sequences of that maximum length. And the problem people were facing with those recurrent neural networks, which end up being always very deep, was that they would not converge. They solved it, and here you will have to watch my talk from last year. They solved it by inventing different recurrent cell architectures, like this. Ooh, that's scary. Let's hide it. But the only thing you have to know is that those new recurrent cell architectures solve this problem of lack of convergence. And since there are many variants, you might ask yourself, which variant is the one that I should be using? For that, let's ask the specialist, what do you recommend?
Well, there are lots of variants, but as long as they have something called a forget gate, they usually perform equally well. And so GRU cells, which are the ones in the middle in your diagram there, are the simplest cells that have this property, and they get the job done.
So that's what you use?
We use GRU cells.
Always?
In general. LSTMs are still being used a bit.
Okay. In first approximation, whenever you build a RNN, use a GRU cell. And don't worry too much about this. All right, let's build something quick. Let's say a language model. This is what I shared with you last year. Let's do it again very quickly. So we have our RNN sequence, and we train it on a sequence of characters. We train it to generate the same sequence shifted by one character. So in effect, we are training it to predict what the next character is. How do we put characters into our vectors? Well, we use one-hot encoding, which is the most basic encoding you can think of. For an alphabet of size 100, you take a vector of size 100, you fill it with zeros, and you mark with a 1 the index of the letter you're encoding, and that's all. What this was doing, so last year we had a bit of fun, and we trained it on Shakespeare and generated new Shakespeare plays. Let me run this again for you. Here we have Shakespeare. company of bastards, how now, my lord, why should I say? There is no more than the manner of my son, which I have said, it was most noted, I weep yourselves, Don John, blah, blah, blah. So it's hallucinated Shakespeare. It's called a language model. So that's one thing you can do. But now Nithum will share the real extent of his work with you. What are you doing?
That's right. So this is the new example that we'll focus on for the next little while. So at Jigsaw, I work on a product called Perspective, which is building a set of tools through an API that can be used to improve online conversation. And today we're going to focus on one of those tools, which is to try and build something that can detect toxic comments. So if you spent any time online, in comment sections, or on social websites, you've probably run into some kinds of toxic comments, things which are rude or disrespectful or make you just want to close the browser and maybe leave the conversation.
And we chose this example because it gives us an excuse to fill slides with profanity and still be okay.
Yeah, and so today what we're going to try and do is build a neural network that's able to detect these kinds of comments.
All right, let's go.
And so the framework we're going to use is the Embed, Encode, Attend, Predict framework. This was introduced by Matthew Hannibal. And basically, it's just a way of encapsulating some of the most common techniques in natural language deep learning into usable blocks that play well with each other.
So Embed will be how do you transform words into vectors?
That's right. In order to do deep learning, you need to transform words into numbers that you can do computations on.
Encode, you will run them through some kind of neural network that will do something?
Yeah, something. Basically, the original numbers you get from embedding might not be the most useful ones, so encoding turns them into more useful numbers.
And that's a neural network?
And that's a neural network that does that.
And then we will talk to you about this new idea of an attention mechanism.
Yeah, not all of the numbers from your second step are going to be equally useful, so attention lets you focus down on the numbers that are the most useful.
And finally, the network will predict whatever it was built to predict. So first, word embeddings. You could also encode words using one-hot encoding. If you have a vocabulary of 100,000 words, it is a possibility to create a vector of 100,000 zeros and mark with a 1 the word you are encoding. It's highly unpractical because it's a really, really big vector. So rather than doing that, we tend to represent words with shorter vectors, which can have continuous values in their values. It's called an embedding. And the easiest way of embedding words is simply to take a big matrix and look up for the index of the given word, what are these values in this big matrix. Initially, this matrix, you will initialize it with a random noise, and those will be your embeddings. Here you see the TensorFlow code for embeddings. So we created this embedding matrix as a variable that in TensorFlow has a very specific meaning, and it means something that will be trained. And we use it using the embedding lookup function. We give it a word index, and it gives us this vector of embeddings for this word. And now what we can do with it is, for example, build a word-by-word language model in the same way as we built a character-by-character language model previously. We can embed words into vectors, feed them through the exact same neural network we had previously, and, for example, train it to predict the next word in the sentence. And when you do that, you realize that not only the network trains, but you start seeing in the embeddings which will be generated, you start seeing very interesting properties. So interesting, in fact, that you will probably be able to reuse this embedding matrix that you generated with this problem for other problems, as long as they involve the same language. So what kind of properties are we seeing there?
Yeah. So as Martin says, anytime you do a deep learning exercise with natural language, you're going to generate some embeddings. And these embeddings can be useful in other problems. So some very useful embeddings that were created were something like Word2Vec by Google or Glove by Stanford. So there they constructed specific problems with the idea of creating embeddings for the words which were maximally useful across a wide range of problems. And these embeddings do have nice properties, like Martin said. So for example, words which are similar to one another, like France and Italy, will appear close to each other in the embedding space. And that means that if your network learns something about France, like how it can be used in a sentence, it'll for free get to know the same or similar things about Italy. Or words like running and swimming will appear close to each other. And so when you solve one of these problems, you actually have three options. You can start with completely random vector of embeddings, or matrix of embeddings, and train them yourself. You can use one of these pre-trained embeddings and just leave them fixed.
But that will work only if there is some similarity between the problem you're solving and how these embeddings were generated,
That's right. If people are using English in a completely different way, then these embeddings might not be very useful.
Okay, so the rule of thumb is if the embeddings were generated for the English language, and you have a problem involving the English language, you're good.
You can usually benefit. Yeah, you can usually benefit from using these embeddings that were trained on English, and there are embeddings for other languages as well. So you can go out and find those. And the third approach you have is to do something like a hybrid approach, where you start with some set of pre-trained embeddings, and then let your model tweak them and train them as you go along. And that's the approach we're going to be taking in our demo.
And there is a setting in TensorFlow when you load your embeddings to tell TensorFlow that this is not a constant, this is something that is initialized but should still be trained during the training.
Yeah,
okay? So that's
right.
how you do it.
That's exactly right. It's just a flag.
All right. So how do you do classification with an RNN, which is what we want to do here? A very typical example is to classify articles, news articles, into geopolitics, economy, sport. And another example is to classify comments into toxic and non-toxic. So you take your unrolled sequence of RNN cells, apply a sentence on the inputs. Now we know how we encode each word in this sentence into a vector. And then simply take the last output coming from the last cell, run that through a softmax layer, and produce a probability distribution across our classes, geopolitics, economy, sport, and predict the class of this sentence. Now, there is a better way with bidirectional networks, right?
That's right.
How does that work?
So when you're using regular RNNs, you only learn the dependencies of each word in one direction. Each word can learn from the words before it, but not the words after it. And sometimes, in your use cases, it's useful to have the whole context in both directions of a word. So there's a simple trick for doing this. You just use two RNNs, one that goes forward and one that goes backwards. And these two RNNs will now give you context, for each word will give you a context in both directions.
And so you obtain two output vectors, and what do you do with them?
Yeah, because now you have two vectors and previously you had one, you can just glue these two vectors together by concatenation, and you'll have one vector again, and you can use this for prediction.
All right. So, but we said we will take this last output from the last cell of this unrolled sequence. All the other cells in the sequence, they also have outputs. Is it okay to throw them out?
Yeah, so that's a good question. So like you said, when we do prediction, if you stop before attention, you still have a classifier and it should still work. But it's only using the output from this last cell, and you're feeding that into your predictor. But of course, there's still information in these other cells, and maybe for long sentences especially, this information might get lost by the time it gets to the last cell. So you'd like to somehow keep this information. Okay, so you can take this information, and you now have the outputs of all the cells. You can do something simple like just take the straight average of these vectors and feed that to your predictor. But it's also true that not all of this information will be equally important. So you might want to use a weighted average. So you want some weights that tell you which words are the most important and which words are less important. And the question is, how are you going to come up with these weights? You could try and learn them from scratch, but that's not so good. You probably want some information about each of the words in computing these weights. The word "the" is probably not very useful, so if the model sees the word "the," it should maybe ignore it. And so you train a little neural network, a very, very small neural network from the output of the cell, whose whole job it is to vote on how important that word is. So this little neural network gets its vote. It gives you a little alpha here, which tells you how important the cell is. Then you do the weighted sum, and then you feed that into your predictor. And that's how you do attention. Attention is just how big these weights are. That's how much attention you're paying to each of the words.
And in this structure, this mini neural network, again, there is only one and is replicated.
That's right. Just like these cells are replicated from time step to time step, this mini neural network is replicated. So it's lovely. You can do the unrolling trick.
All right, so we have all we need now. Oh, no, maybe you want to normalize your attention vector?
Yeah, so that's the last important trick, and it's just a technical trick. These alphas, when they come out of the neural network, can be anything. They can be negative, they can be positive, they can be big, they can be small. So again, we're going to use softmax, and this will just turn them into numbers between 0 and 1 that add up to 1. So that'll make for a nice weighted average.
So are we ready to build a toxicity detector?
Yeah, so now that we have these 4 steps, we can build an end-to-end toxicity detector just using them. So let's just review. We start with a sentence. We then do the embedding. So we turn these words into a vector of numbers. Here we're going to use glove vectors that Stanford published. Then we're going to do the encode step. So here we're going to feed these embedded vectors into a bidirectional RNN. And again, you're going to get 2 vectors at the output of each cell of the RNN. And so you concatenate them together to get 1. You feed this into your little attention network in order to get votes for how important these are. Then you do a weighted average and feed it to your predictor, and you get a decision as to whether or not something is toxic. And that's it.
And that's it. Wow. No, maybe not. One question I always have when I see these diagrams is my sentence here is exactly 6 words, and I see an unrolled sequence of exactly 6 cells, but in real life, it's not as easy. Your sentences have different length. So usually the way this works is that you have to use some padding. But I want to share with you this function, dynamic RNN, that was quite recently added to TensorFlow, and which is very useful because with this function, you don't have, this function is what does the unrolling of your RNN sequence. So you give it 1 cell, and it produces a sequence of that cell unrolled across a certain number of steps. But it's very, very practical because if you are processing a whole batch of sentences, of course, none of them are the same length. Using dynamic RNN, you can give it the batch of sentences, give it another vector which contains the length of all those sentences, and in the batch, it will automatically unroll the sequence exactly the correct number of steps for each sentence. And why that is important, it's because when you have your sequence, the output state that was generated at the end of the sentence is actually very important. And here, dynamic RNN will give you in the outputs the output state that was generated exactly at the end of your sentence, and not at the end of your sentence plus some empty cells running in the void. So now we are ready to build this toxicity detector.
That's right. So now we're going to take the diagram that we saw earlier and turn it into code. So the first step in the diagram is to do the embedding, and we've already seen this function, embedding lookup. So this just takes 2 variables. One is the words that we're interested in embedding, and the other is a matrix. And this matrix you can just load from a CSV file. So you can go to Stanford's website, download their glove embeddings, and load that CSV file into a variable in TensorFlow, and then use the embedding lookup function. The next step is the encode step. So here we want to pass these vectors, these embedded vectors, through a bidirectional RNN. And like we said before, you have to tell the RNN what types of cells you're going to use. And so here we're going to use GRU cells. And here you notice that we're defining the GRU cells twice. And that's important. You want to define 1 forward cell and 1 backward cell because you don't want them to share parameters. You want them to learn different things. And so once you've defined these 2 cells, it's a matter of just tossing them into this bidirectional dynamic RNN function.
Which is the same as the dynamic RNN previously, but for bidirectional RNNs.
Yeah, it's basically exactly the same. And there you just tell it which 2 cells to use and what you're feeding in, which is your word vectors that were embedded previously. And then, like we said, this produces 2 vectors for each word, so we're going to use the concatenation to combine them. And then you're just going to use attention. Now here, we're cheating a little bit because I wrote a function to compute these attention weights. But you'll see that it's not a very complicated function. In fact, we're going to show it to you right after this slide. And then the final step, the predict step, is, again, just one usually very small dense layer that has output 2 because we have 2 classes, toxic or not toxic. And then the prediction is just which of these 2 classes is bigger, or which of these 2 numbers is bigger, which is what the argmax does. And then to compute the loss and train the network, we're going to use the softmax cross entropy that we've always been using.
So argmax, we haven't seen it yet. It's a function that in a vector tells you the index of the biggest element.
Exactly right. Yeah. And so that's the embed, encode, attend, predict framework. This is basically all the code that you need to train the model function of your neural network. And the only missing piece was this myAttention function that I had to split out into another slide. But you'll see that it's a very simple function. Again, it's just two dense layers back to back, and then a little bit of reshaping in a softmax.
So basically a two-layer neural network, dense neural network.
Yeah, a very small two-layer neural network, whose whole job it is to compute these votes for how important the outputs of the cells are.
So you're telling us that in your job you get paid for producing 10 lines of code.
Absolutely, yes.
Fantastic.
And so, yeah, now it's time for a demo.
Yeah, let's go.
So we trained a toxicity classifier in a Jupyter notebook for just a few minutes, and we were using publicly available data on Figshare. And the link to this data will be in the slides notes.
So we start with a very nice fuck off, you idiot.
Yeah, this is a little function that tells you whether or not the computer thinks that the sentence is toxic or the model thinks the sentence is toxic. And another nice thing about attention is it gives you some kind of interpretability because it tells you what the model was paying attention to. So for this sentence, the model thinks the sentence fuck off, you idiot is toxic, and it's paying attention to the words fuck and idiot.
Great. Let's try something else. Thank you for your help editing this. This should not be toxic.
Yeah, some of these are real-world examples. The model, again, correctly determines that this is not toxic. And you can see that the attention is sort of spread out throughout the sentence. It's not paying attention to anything that much in particular.
All right, let's try something without an obvious curse in it.
Yeah. So by now, maybe you're thinking that this is just a bad words detector. So we'll try something that's not quite so obviously a bad word.
I'm going to shoot you.
So this is more of a threat. And again, the model thinks it's toxic and pays attention to the word shoot. It's noticing that the word shoot is maybe being used as a threat here.
So maybe it's just detecting shoot as a curse word.
Yeah, perhaps it is. Let's try another sentence with the word shoot.
Oh, shoot. Well, all right.
Okay.
And that is not toxic.
Yeah, it's still paying attention to the word shoot, but here it doesn't think it's toxic anymore. And now we'll try another sentence where there are only positive words, except that they're kind of negated.
You're not that smart, are you?
So here there's nothing obviously negative about it, except if you understand that not negates a sentence. And here it's able to detect that this is toxic without really knowing, finding any particular bad word.
And if I try you're very smart,
yeah, and
which
you
is
see
a positive comment.
You see that it's paying a lot of attention to the word you're. So we'll try another sentence with you're and smart and see how it does. And here it's able to say that it's not toxic.
And
it still pays attention to you're, but it's not toxic. Yeah. And so in about 2 slides worth of code, we were able to build a detector that does a pretty good job of distinguishing these things.
And that uses the attention mechanism that is a big part of why it works so well.
That's right.
So let's continue. Now we will, I started with Google Translate. Will you believe me if I tell you that Google Translate is not 6 lines of code, but 10? Let's see. Let's see if we can build it. So this is how you would build a translation neural network. You have 2 recurrent neural networks which you tag back to back. One is called an encoder, and the other one is called a decoder. And you will feed an English sentence to the first one, then feed the output state of this one into the second one, and the second one will generate a French sentence. There is always a lingering question, which is what do you put on the inputs of this second neural network? And we'll get to that in a minute. It's a bit complicated, but during training, it's actually very simple. What is supposed to be happening, a little bit like in the language model we saw previously, each one of those cells in the decoder is supposed to produce a word and to produce an output state, which is fed into the next cell, and you are supposed to feed also the word that was produced before as the input into the next cell At least that's how you train it. But people have noticed that instead of actually going through this softmax layer and computing exactly what the word is, it works even better if whatever your half-trained bad network predicts, what you put on the inputs here is the correct answer, is immediately the correct answer. So the correct answer during training will appear in two places, once here on the inputs, and a second time in the loss function. So it will be used in the difference between what the network predicted and what you know to be the true answer, which is its normal place. Isn't it a problem to be predicting, sentences like that? Because if I look at it, I see this softmax, little layer, and that produces a probability across my entire vocabulary.
Yeah.
So it produces vectors of 100,000 elements.
Yeah, that's right. In the previous problem, we only had to predict two things. Now you have to predict something massive. And computing this every time you're doing a training step is extremely expensive. So there are shortcuts. And TensorFlow has a nicely implemented shortcut called sample softmax loss. And all this does is, instead of computing the entire softmax, it computes an approximation.
Because you don't actually need the output sequence sentence here. The only thing you need is the loss.
Yeah, you in fact need the loss or even just the gradient of the loss.
Or even just the gradient. So the way they did it is that they wrote those gradients and then tried to optimize them to compute an approximate gradient that still trains. And there are many different ways of doing that. It's just an optimization. In TensorFlow, you can use this sample softmax loss function for that. During training. During inference, so when you are actually predicting something, it's a bit more complicated. So once you have trained this network to actually translate a sentence, you feed into the encoder, the cat ate the mouse, and you have an output vector here. Then let's look at it through code. I like reading code. I'm a developer. Then I will feed this input vector into my first decoder cell. And this decoder cell needs also something on its inputs. It's this Go token, which is like a word. So I need to embed it, which is why I use embedding lookup. Then I run this through my cell. Dynamic RNN can run something through one cell if the input is of size 1. And this gives me an output and an output state. Then I implement my softmax layer here. So that's a dense layer in a neural network, followed by a softmax activation function. And this activation function gives me a probability across my entire vocabulary of what this word is supposed to be. So if I have the probabilities, I can say, well, let's pick the most probable word. That's argmax. And I have my word. Next thing, I feed this word into the next cell, and I feed the state into the next cell, and continue, and doesn't look like a very good translation. Can you debug this for me?
Oh yeah, so this is a kind of a classical error. What you're trying to do isn't to try and predict the next word that's the most probable. What you're trying to do is predict the most probable sequence of words. And at each step, you have a conditional probability of what's the most probable. So in trying
knowing what came before.
Knowing what came before.
Okay.
So in trying to predict the largest sequence, given these sort of conditional probabilities, this is, again, a well-studied problem in math. And instead of just using the argmax, you can use something like beam search. So TensorFlow kindly implements beam search for you.
So that's a bad idea.
That's a bad idea.
I have to use beam search, which is available in the sequence-to-sequence API, and I have a good translation. Thank you. And we won't go into the details of how beam search works exactly. It's not that it's super complicated, but this is just a super standard problem. Most probable sequence from conditional probabilities has been solved multiple times. Use the function. Now, can we add attention to this?
Yeah, so
I'll let you do this.
It turns out that the previous model works fairly well. But if you try and add attention, you can get an extremely good model. That's part of the reason that Google Translate is so good today. So let's say you start with the black cat ate the mouse, and you feed if you're doing the decoding step, you're going to feed the output of this cell, or the state of this cell, into the decoder. But there's a problem here. In fact, there's a couple problems. One is, you're taking all of the information from this cell, and you're turning it into just one vector here again. And we already saw why this is kind of a bad idea. You're losing all the information from these other cells. And you're feeding it into this cell, and you're basically trusting that cell to pass it on to all the future cells. So again, for very long sentences, this might not work very well. All right, so what can we do about losing the information from these cells? Well, we've already seen the trick. Let's just compute attention. So again, let's just use the outputs of all of these cells, have them vote on how important each of them are, and then do a weighted average. Okay, that's pretty good, but we can do even better, because in this context, we actually have an additional piece of information. We have the output of this cell here. So why don't we use the output of this cell to also help compute the attention?
And so that cell is the word that is currently being translated.
Yeah, it's the decoder's attempt to translate the next word. So we feed that as additional information. So now when these little blue boxes are doing the voting, they're voting with both knowing the word that they represent and the word that they're trying to predict to some extent.
So you've seen what happened here. We had this blue box generating attention from the output of the encoder cell, and we changed the blue box a little bit to accommodate for bigger inputs, and we added a second input, which is the output of the decoder cell.
Yeah, we made it a little bit fatter at the base.
Yeah, like this.
Great. So now that we have this weighted average, what are we going to do with it? Well, it turns out we can feed it into the new network in a couple different places. Okay, so maybe the weighted average this time puts all of the weight on this word cat here. That's pretty useful. So let's feed that to our network. Firstly, we can take the output of this weighted average, take this hidden layer, put them together with a tiny neural network, like a one-layer neural network here, and feed that to the predictor. So this neural network sees the word cat, sees the word cat, and sees whatever the output of this cell is, and it's able to correctly predict Shah. And then the other thing we can do is take this attention vector and feed it into the next cell. So the next cell gets a bit of a hint about what we were paying attention to previously.
And the next cell, so if you click, now I see a problem there. You're cheating, because up to now, we always had those RNN cells with one input, one output, one input state, one output state. How can you make one with two inputs?
Yeah, well, it turns out that we can use our old friend concatenation again and just make the cell a little bit bigger. So here, the input from the word Shah is going to be an embedded vector for this word. And then we can just make the input cells a little bit bigger by concatenating also the attention cell that we got from the last step.
And so the first cell, if it has two inputs, what is on the second input?
Oh yeah, so you notice that there's no red arrow here. But this cell has to be the same shape as this cell. So we're going to fake a red arrow with just zeros.
Oh, okay.
Yeah, that's all. We're going to start with 0 attention. And then you could keep going. And so you see that the second word pays most attention to the word black here, noir, and then the word 8, and then the word the mouse. And you get to see something in this sort of picture of what the network is paying attention to. You get to see some cool features of the language, like the fact that...
So here we are visualizing the values of alphas.
That's right, yeah. We're
darker color is big alpha, right?
Yeah, okay. That's right. Darker color is the closer alpha is to 1. And you see cool things, like the word black cat gets reversed from English to French, or the word 8 gets expanded to 2 words. So attention is really nice because not only does it make your network better, but it lets you interpret some of the results.
So, who thought this was a bit complicated? Couple of you. This looks like 100 or maybe 200 lines of code to implement, right?
Well, maybe. We'll see.
Let's see. So, let's first embed our words using embedding lookups. Then we need a GRU cell for our encoder, and actually just to show you that these cells can be wrapped to implement various regularization techniques like dropout. I put a dropout wrapper around it. And then I use my dynamic RNN to unroll this encoder cell. So here, basically, I implemented this part, the encoder. Then the decoder is, again, a GRU cell. I will use this beam search trick to produce from the unrolled decoder the most probable sequence of words instead of just the most probable word. And in my sequence-to-sequence API, I also have a dynamic decode function to which I feed my decoder cell, and this will unroll the sequence and build my decoder. So now I built this part. And the only thing missing is the attention mechanism. So this is how the attention mechanism works in the sequence-to-sequence API. This GRU cell here is a repeat from the previous slide. This is my decoder GRU cell. I will do a little change to it. In this API, I can wrap it with an attention mechanism. And in the code I'm writing, the only place where I'm instantiating something a little bit complicated is here, the Luong attention. Here I'm actually instantiating a certain little neural network with a given shape that has been devised by Mr. Luong, and that works well in this case. So let's use Luong attention. I wrap my cell in Luong attention, and then I use this API, the sequence-to-sequence attention wrapper. So that's what I write. I wrap it. Here I just instantiated my attention, and I wrap my cell into this attention wrapper to obtain my decoder cell. And then I just plug this decoder cell wherever my GRU cell went previously in the decoder. That's it. That's the entire implementation using the sequence-to-sequence API in TensorFlow of this sequence-to-sequence model with attention. And it's exactly 10 lines of code. So yes, Google Translate is actually 10 lines of code. We are skipping some of the glue code that loads the data in and all that. And yes, Google Translate has a few more lines, but let's see if this actually works, if this translates something. So let's go. I have a script on this machine that runs inference on one file containing German sentences. I will show you in a minute which sentences. And let's clear the screen so that you see it more clearly. Können Sie übersetzen? Can you translate? Ich verstehe nicht. I do not understand. Könnten Sie wiederholen? Do you repeat again? Yeah, almost. Die Konferenz wird von Computerenthusiasten organisiert. The conference is organized by the Congress. It got it wrong on this one. So, yes, be reassured for the jobs of people working on Google Translate. What they do is more than 10 lines of code. But with these 10 lines of code, we are translating German to English in a pretty impressive way. And that's mostly thanks to this attention mechanism. So this is, this is significant. What we are sharing here with you was published in a blog post from Google Brain. And they built the sequence-to-sequence API to be able to experiment very easily with different architectures of recurrent neural networks. And so you have seen a couple of them, one for detecting toxic comments, one for translating. And you see that, again, it's a game of Legos where you piece together different pieces. And TensorFlow now has very efficient APIs like sequence-to-sequence for doing these pieces in a simple way. And indeed, those models end up being 10, 15, 20 lines of code, which is really very, very nice. So we can translate. A little word from the future. Now, what is intriguing for me is that when I see good translations, I think about a translator and think what you need to do to produce a good translation. You need to understand the text. Can you translate mechanically? That doesn't work. A good translator needs to understand the text to be able to translate it into a new language. So, do you think that this network is actually understanding the text?
It's difficult to say.
So let's try an experiment. That is an experiment that has been published in a paper by Oriol Vinyals. And he said, well, let's take this neural network for translations. And now, instead of training it on pairs of English and German sentences, let us train it on movie subtitles, dialogue. Instead of translating, it's going to generate the next line in the dialogue. And I wanted to show it to you live, but unfortunately, it hasn't yet finished training. But I'll show you anyway. It's kind of hilarious. It doesn't do what I want it to do, but let's see anyway. And here, instead of movie dialogue, we trained it on tech support transcripts. So it will be generating a lot of computery stuff about tech support. Let's see. Nope, not this one. Almost there. Yeah, this one. So is it a security problem to disable antivirus? Yes. Does allowing connection to anyone means that the system will acquire EP from network before system startup password has been entered? That's not a good idea. Weird. It is. And then I tried to troll it a little bit. So I said, what is the meaning of life? And it answered, yeah, I have no idea. Which is kind of fun. and then, well, just to show you that it's not yet so good, I asked how many legs does a cat have, and it answers, yeah, I have to use the output of the desktop and see if you have to run the same partition. No, 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 not the point. But in this paper, Oriol Vinyals, he publishes the answers he got from a movie dialogue database, and I find it fascinating. How many legs does a cat have? 4, I think. How many legs does a spider have? 3, I think. It got the answer wrong, but the answer makes sense. The number is wrong, but syntactically it's correct. There is a number, and in one of those two cases, it's even the correct number. And when asked what is the purpose of dying, it says to have a life. Kind of interesting. What is the purpose of being intelligent? To find out what it is. These are certainly cherry-picked examples, but what I find exciting here is that it's for the first time, you see here an interaction with a neural network that produces, well, not completely a human-level type of interaction, but an interaction that shows that it has some knowledge embedded in it, and it is able to express this knowledge in response to meaningful questions. And this knowledge is entirely contained in the weights of the neural network. So it's stored in it in the same way as we store knowledge. If you compare this to the way that we do chatbots today, it's really completely different. To do any chatbots are basically a first very powerful neural network that decodes the spoken language, a second one also very powerful that parses the sentence and finds the verbs and adjectives and all that. So this is all state-of-the-art, super powerful. And then after that, you have someone who tries to map whatever was parsed to a SQL query, and that's basically an expert system from the 70s, which is known not to work great. And that's why you get this kind of mechanical interaction when you ask a question. Sometimes you get an answer, sometimes when, it fell through the cracks and there is no hand-coded mapping of what you said to a SQL query. It says, I can't help you with that. Here, all the information is contained in the neural network. Of course, here you have the opposite problem. A SQL query is kind of useful because you can insert a given piece of information into a database very easily. How do you insert a piece of information into a neural network if it is missing some piece of information? Well, there is a second paper that was published, which I find also quite fascinating. What they did is that they found a corpus of news articles. And they were summarized in bullet points at the end. So if the article would say, the President of the United States visited some country and met the prime minister and blah, blah, blah. At the end, you would have a summary in 5 bullet points. The president visited France, he met the prime minister, and so on. And they said, well, these bullet points can very easily be turned into questions. If the bullet point says the president visited France, you can transform this into the president visited X and ask the system to solve and train the system to solve for X, knowing the text. So that, when trained, is actually a neural network that can read an article and answer questions about that article. And here I'm showing you some of the outputs. Look at this article about Dolce & Gabbana, the way they did their latest fashion show. The question is, who dedicated their fall fashion show to moms? And the neural network correctly answered Dolce & Gabbana. And if you think this was easy, look at this one. This is an article about a Navy SEAL who died in an accident. The question is basically who died. And you have a host of things, of names, which could be good answers, like the right answer, Jason Quartz, that's his name. But Paris, California, Riverside, US Navy, CNN, Highlands Ranch, Colorado, all these are names, and you have to understand the article to actually pick the correct name out of all those candidates, which you could have implemented something simple that just says, well, if you see names, it's one of those. And here again, this neural network correctly identifies Jason Quartz as being the good answer. I don't know where this is going, but on one hand, we have a way of embedding information in a neural network in a way that produces natural interaction where this information can be surfaced. On the other hand, we have this research that has built a neural network that can read text and answer questions. I don't think anybody has yet connected these dots, but I wanted to share this with you because I find this research quite fascinating, and if you ask me how far we are from the singularity, I will still answer, well, I have no idea. There are too many steps, and we haven't mapped even a tenth of them. But I think with these things, we made one of those small steps. It keeps me quite excited. How about you?
Well, there's lots of interesting research in learning facts about the world, having memory. But one of the most exciting fields in deep learning at the moment for me is reinforcement learning, which is what Martin will be talking about right after the break.
Thank you. So 10-minute break again, and after this break, we come back, and this time for reinforcement learning. Where is my reinforcement learning slide? Somewhere. Well, what time is it? 11:45, so 5 minutes before 12. Please be back here for the last half-an-hour session on reinforcement learning. Thank you.
Thank you.